This is last section of chapter 6, bond energies to find enthalpy changes of a reaction. So when a bond has to break before it can be made. Energy changes are due to bond breaking, which requires energy, which is endothermic, and forming bonds, which releases energy, which is exothermic. If the energy to break the bonds is less than energy to make new bonds, it's exothermic. If the energy to break the bond is greater than energy for new bonds, it's endothermic, so positive energy. So here are two examples. We have a combustion reaction of methane. You should know that's exothermic anyway, but the energy to break the bonds is smaller than the energy to bond as you go down, so the energy released is made up the difference, so it's exothermic. Here, to react hydrogen bromide with each other, or to decompose hydrogen bromide, which again you should know a decomposition is endothermic. The bonds to break are greater than the bonds forming, so the energy that is needs to be on the reactant side, so it's endothermic to counterbalance the breaking of hydrogen bromide. In reality, not all bonds in a compound are broken then reform, so that means not every reactant is broken. Some bonds in reactant are broken and new bonds are formed in specific sequences. We'll get to this later when we talk about reaction rates. The minimum energy required to break a certain bond is the start of the reaction, which is called the activation energy. So you have to have enough energy to break the bonds for the reaction to occur, and that's the activation energy. So bond energy is the amount of energy needed to break a specific covalent bond. The energy of a CH bond, of a single bond between carbon and hydrogen atoms, and there's also energy to break diatomic elements. So Br2, for example, is broken apart into two bromide atoms. It's endothermic. You can see it's 193 kilojoules per mole. Here's double bond oxygen. Again, all bonded energies are endothermic, meaning that you have to break the bonds. Hence plus sign because in front of the bond energy. When new bonds are formed, the amount of energy is released, so it's negative amount. So if it forms oxygen bonds, it would be negative 498. Bond energy is affected by other atoms as well. So here we have a water molecule has two OH bonds. Here you have ethanol, which has one OH bond, and then 1, 2, 3, 4, 5 CH bonds, a CC bond, and a CO bond. So it's 1, 2, 3, 4, 5, 6, 7 bonds you have to account for in a molecule for ethanol. The more energy it takes to break the water OH bond than the second OH in water because of electronegativity. We can use bond energy to calculate the enthalpy change of a reaction that cannot be measured directly. The equation is easy. It's broken before formed, so it's broken minus formed. So you have to break bonds before you can form the bonds. Easy way to remember it. So the total amount of energy for the broken, which is the reaction side, minus the total energy of formed, which is the product side. Here's an example. We'll go over this in class, but you have the production of ammonia from nitrogen and hydrogen, and the bond energies of triple bond nitrogen is given, hydrogen and NH is given. You can try this. The combustion ethanol, so C2H5OH combusts with high oxygen to make CO2 and water, like any other hydrocarbon combustion reaction. It's important to rewrite the equation using bond drawings so you can see exactly how many bonds of each substance there is. And the bond energies can be calculated using the following bond energies on the lower right hand side. You have the CC, CH, CO, double bond O, double bond CO, and OH. And that's it.